Hey everybody, it's Taki 117 here with Taki's Space Program. So, we have some contracts that we picked up last episode. Ferry a couple tourists, perform the Luna 3 mission, and have a communication satellite for the inner planets. So, what we're going to work on today is this communication satellite. Before we get too far into it though, I want to upgrade my Research and Development Center so that not only can I EVA and collect surface samples, but I can also transfer resources, and it ups my science limit to 500, so that I have more of the tech tree that I can unlock. Now, I'm not too worried about, warping to completion of that one, and that one really doesn't matter. I am, however, going to launch I'm going to move my inner planet communication satellite to the front of my build list so that it gets built first, because I really want to get that into orbit, because it's not just for the inner planets. It can also be used for lunar communication as well, and that's going to be really important later as I progress through the tech tree. So we're just going to go ahead and warp to that. Now, this satellite is different than any satellite I've designed before. It's got, it has your solar panels, it's got antennas and things, but it's actually built around a probe core. The whole thing is a probe, not just like one little section. So, I'm going to roll it out. This is actually going to be a beautiful daytime launch. Now, I'm not worried about putting the satellite in any specific orbit. The only requirement for the contract is it has to have a periapsis greater than, I believe it's 600 kilometers, which is easy enough to do. Let's wait on this to load up here. There we go. So we have about 4 kilometers of delta V in our first stage here. And just checking my communication satellite here. So yeah, it doesn't even say it has to be anywhere. So, what I'm going to do is I'm actually going to warp to the night side. This is going to be a night launch, specifically because it doesn't have a whole lot of battery power. When designing this, I didn't really plan ahead that much. As you can see, my satellites are moving around. So this is going to be, looks like a little after midnight. Look at that beautiful illumination on my rocket there. So the sparklers down here don't actually ignite the engine. What they do is they burn off excess hydrogen that has the potential to leak out through the engine prior to launch. So, launching in 5, 4, 3, go from engine start, 2, 1. Mission and lift off, maybe? Ow. And we have a problem. Oh dear. Oh dear, oh dear. That's not good. So, what's happened is I've actually left my boosters on the launch pad, which is not good for obvious reasons. But we're going to try to make orbit anyway, because now we're up to about 5 kilometers a second of delta V. The only problem is my rocket is not going nearly fast enough. So at the moment I'm trying to stay vertical, which I'm actually doing a pretty good job of. There is a little bit of slide because my velocity vector is off center, but it's not so much that I can't compensate. I'm going to see if I can roll just a little bit here without screwing up too much. Okay, here we go. Alright, so now I'm starting to pick up speed. My velocity vector is coming back to vertical, which is good. I want my rocket pointing up. So I might actually be able to save this mission. Now, this is an Atlas rocket. Originally, the booster section that I accidentally left behind on launch pad there was supposed to come with me and provide a little bit more thrust-to-weight ratio during the first couple of minutes of flight, and then it would fall away, leaving the center stage here, which would carry me most of the way to orbit. Unfortunately, that didn't work as planned. So as you can see, I'm now trying to correct my mistake here. And okay. So we're good. We're good. We are back on our flight path. Roll this way. To roll 90 degrees. Now, as you can see, our inclination is about 28.6 degrees. That's going to drop just a little bit because we are back on glide path, but we still have plenty of delta V to get to most of the way to orbit. And I'm actually going to hasten this just a little bit. So as you can see, our thrust-to-weight ratio is going up rather nicely. We're at 1.58 right now, or thereabouts. I'm actually going to come down to 45 degrees. As we're at our 10-kilometer benchmark here. And there we go. Okay, back on glide path. So, that was a little harrowing. I was expecting this rocket to kind of fall apart on the launch pad. Fortunately, I had a thrust-to-weight ratio greater than 1 on the pad with just the center stage. So that's always a good thing. Oh, look at that. There we go. Beautiful, ascending into the night. Beautiful rocket. So, here we go. Alright, so we're at 21 kilometers, which is good. We are actually right on the glide slope. I'm impressed. This launch is not going as badly as I had anticipated, which is good. So, now, the reason the plume is expanding as it is, because if you notice, as we were leaving the launch pad, it was very compact, and now it is very wide, is because the atmospheric pressure is less. Reason for that is as you increase in altitude, atmospheric pressure drops off. Eventually you reach a point where atmospheric pressure is essentially vacuum. It's not vacuum. There is still some pressure there, but it is effectively vacuum. See my fairing heating up a little bit there as we push our way through the atmosphere. Now, most rockets in real life are designed for a continuous burn to orbit. What they do is they'll perform their, they'll launch, perform their gravity turn, and they just keep burning and burning and burning until eventually they reach kind of an orbit. There are some specialized engines that are able to be restarted, and you can turn them off and back on again. But for the most part, rockets just burn to orbit. So I'm going to put this one in a... Oh dear. Oh dear. That's not good. So something just exploded on my rocket. And I'm going to hit F3. Oh dear, my Communitron 8888 burned up from overheating, which is the whole point of this rocket. Yep, that's gone now. Okay. Well, poop. So, we are going to orbit prograde, ditch this fairing, we don't need it anymore. We are going to deploy these solar panels while we have some power, because right now power is quickly running out. Or, well, not quickly, but it is certainly in our best interest. We are going to activate our long-range local antenna and activate our medium-range local antenna, and we're going to ditch that first stage. Now, because we are still sort of in the atmosphere, that first stage is hanging out with us, because the decoupler here doesn't provide a whole lot of impulse to push my satellite away. But as you can see, as we move, it's going to drift farther and farther away, and it's eventually going to fall back to the planet. Oh, that scared me. Okay, here we go. I don't need the node editor. I need the maneuver planner. There we go. I need that one. Because I want to circularize at the next apoapsis. I'm going to create and execute that node. As you can see, I'm producing more than enough power for these two satellites. And there goes my booster stage there. So, this flight has been fraught with problems, but you know what? That's okay. Because it is still a successful mission. I'm still going to have another communication satellite capable of self-sustaining. So it's just a better satellite for my network. Okay, so we still have... There we go. There's that tiny little engine firing, pushing my periapsis up and out of the atmosphere and circularizing my orbit. So, originally the satellite had a dish on it, but unfortunately that burned up during ascent. The main reason it burned up was there's a gap in my fairing. It's usually not a problem. But as you push through the air heats up, causes whatever's catching it to heat up, which has the potential to cause that particular part to overheat, which it did. So, unfortunately, I have to build another one. But you know what? I have a viable rocket design. It works. It gets to the orbit that I wanted it to get at. And so now it's just a matter of, well, making it... It's a matter of adjusting the flight profile. Actually, I want to turn the other way. And there we go. So we now have a satellite that is consistently pointed at Earth that can communicate omnidirectionally, as we can see here. So let's go back to the Space Center. Let's build another one. Let's go ahead and launch it. Again, this is going to be another night launch. Like I said, it doesn't have the electrical capacity to survive a daytime launch and still have enough power left over for a nighttime boost to orbit. So I'm building the exact same rocket. I am going to adjust my staging a little bit, just so I don't have the problem I had with this launch. Basically what happened was I dropped my boosters when I was supposed to drop my launch clamps. Launch clamps are there. And this does have the lights and cameras. So we're just going to build. It's going to take a little more than 2 days. Which, not a big deal. Tourists can wait. My other missions can wait. But it's really nice to just have the communication not only to the moon, but also to, you know, the inner planets. If I do decide to go interplanetary, and I will eventually get there. It's just a matter of fuel more than anything. It's a matter of timing and just having the communication. Because if you don't have communication with an unmanned probe, you can't control it, and it's lost in deep space essentially forever. The R&D building is complete now, which is nice. I have more nodes I can unlock. That's for future episodes, of course. Just finishing up this communication satellite build here. Rolling it out, and this is not going to be a night launch, unfortunately. Or not set up to be a night launch initially. I will have to warp to make it a night launch. But we will do that on the pad. So here we go. We are on the pad once more. Here we go. Take a good look now, because in a couple of minutes it's gonna be dark. I'll find it. There it is. So you have so many probes zipping around, it's kind of hard to keep track of which ones are where. You can see my internal communication, or my inner system communication network has kind of become a little lopsided, but I'm not too worried about that. So here we go. Switch to our launch camera. So, launching in 10, 9, 8, 7, 6. Go for main engine start. Start. 3, 2, 1. Lift off. That's what it's supposed to look like. Again, still having some issues staying vertical, but it's a lot better. Oh dear. The good news is this rocket is mostly aerodynamically stable. You know, if I tell it to go a particular direction, it's gonna go that way, and it's gonna return to stable flight more often than not. Problem is getting it to stable flight. So as you can see, I'm constantly trying to fight it because, well, I screwed up my gravity turn. Fortunately, I have enough thrust to weight ratio. I can basically tell this rocket where I want it to go, and it will go there. Unfortunately, alright, let's just point you up. There go the boosters. I don't need them anymore. Okay, here we go. We're pointing up now, bringing our velocity vector back to center. Now we are at 8 kilometers. Okay, we are back on glide slope now, mostly. Now as you can see, I did manage to save that rocket launch, but normally NASA would have just detonated the rocket and been done with it. Unfortunately, this is not NASA, and we have the ability to try and save our launches. Do want to roll to 90 degrees, however. The main reason I'm rolling to 90 degrees is so that these small vernier engines on the side here have a greater range of thrust. As you can see them moving all around when I go to adjust my pitch and whatnot. So we are at the point now where I can follow my orbital velocity. Instead of my surface velocity vector. It's a little more accurate. Again, this one is going to the 900 kilometers that the... well, it's going to 1 megameter or 1,000 kilometers, but the other one ended up a little short at about 990 something kilometers. Not important. This one is going to about that. Again, I have tons of delta V in the actual satellite, but I am going to wait until I am out of the atmosphere to perform that maneuver. As you can see, my apoapsis is clearly on the clearly on the day side of Earth. Alright, so we are out of the atmosphere. I'm going to go ahead and bring up my maneuver planner. I'm going to ditch these fairings, and this is what the satellite is supposed to look like. Can I not select that solar panel? Ah, there we go. Okay, extend that panel. I'm going to extend that panel. There we go. We are going to ditch our first stage, activate our inner system antennas, and we're going to save this main antenna for when we're actually on orbit. So we are going to change apoapsis to 1,000 kilometers at the next apoapsis and create and execute that node. Oop. So, here we go. This is probably going to be a substantial burn. Because not only am I circularizing, I'm actually going beyond that to adjust my apoapsis. Here we are coming over Africa now. And I do still have quite a bit of monopropellant left, which is good. I was afraid I had used some in my frantic attempts to get this rocket ascending properly. And we are going to accelerate this burn just a little bit. So you can use physics warp while burning your engine to accelerate your burn. I don't advise doing this with anything larger than a probe or some other small spacecraft. It's not designed for use with large ships. Mostly because it increases the physics calculations done, which increases the stresses on the joints, and large ships can break apart. Even small probes can break apart. There we go. We are at 1 megameter, so we are going to circularize at the next apoapsis, because that is our furthest point. We're going to create and execute that node. Now we are in a stable orbit, so if I am unable to execute this because I have run out of power, it's not a big deal. It does, however, look like I'm going to have plenty of power to execute this maneuver. As you can see, it's only an 8-second burn because we did a majority of our burning while we were still in the atmosphere with our main booster stage. And then we just adjusted our orbit at apoapsis, and as you saw, it took us a lot more delta V to do that. Whereas if we had done it at periapsis, which at the time was still inside the atmosphere and it wouldn't have worked anyway, but if we had done it at periapsis, it would not have taken us as much delta V. 2 and 1, and there we go. We are in a stable orbit. We are going to point, let's point radial out, and we are going to set this target as Mercury, which is the farthest planet away from Earth, traveling in towards the Sun. We are going to activate it, and we're going to sit here for a few days. So while we're doing that, I'm going to go ahead and finish building my other rockets. I'm going to design some other missions that I want to do, and I will see you next time. Until then, I'm Taki 117, and remember, it's just rocket science.